The next part of our solutions, acids, and bases unit we're going to take a look at is called preparation of solutions. So initially, I want to start you out by looking at some components of glassware in the lab. Because now, at this point, you're going to be getting into the lab and using more and more of this equipment, you should be very familiar with what each thing is called and how to use all of these pieces of lab equipment. So I have a document that looks like this. You can get it on your workspace. And I would like you to go through and try and figure out how to label each of these different components of glassware. Now, try not to use the internet or textbooks or anything like that, and just attempt to see how many you do know already. Then, once you feel like you have named as many as you can either use the internet and fill in some of the blanks. Then I've also posted the answer key to this that you can either get from your teacher or get off the workspace. And you can fill in all of the remaining that you either missed or were unsure of, or maybe got a little bit mixed up on when you went through to name these. Now, try and be specific as to what you're looking at when you take a look at these. And what I would recommend too is if you are unsure of what the glassware is used for. So for example, I'll give you a hint. Number 11 is called a burette, and we use a burette for titrations. Now, if you're unsure about what a titration is, that's okay. We're going to do a titration in the next unit. But what I would say is maybe jot down not only that number 11 is a burette, but it's used for titrations. Or for example, number 10 is a pipette, and pipettes are used for precise liquid measurements. So maybe help yourself out, give you an example of what each of these pieces of glassware or lab equipment is used for, and that will help you as you go through both the remaining portion of this course and Chemistry 30 and beyond. So try again to go through this glassware on your own, then use something in addition to help you through it, and then get your answer key and check your answers, see how you did. Now, preparation of solutions from a solid. So what we're looking at is creating a solution that we can use in the lab for any sort of experiment or test that we might be doing. A standard solution is a solution of just a very accurate concentration. Now, we use these in a variety of industrial processes and in labs, and we require very accurate equipment and judgment to measure the mass of a solvent and the volume of a solution. So we want to use accurate scales to measure mass. We want to have a variety of different glassware pieces that we can use to measure an accurate volume of a solution as well. So as you go through, you should now be pretty familiar with some of your glassware, or at least try to be familiar with that glassware to learn how we can prepare these standard solutions. Now, initially, we have the preparation of a solution from a solid, and you might recognize this as being kind of familiar to what we talked about when we calculated some of our concentrations in our previous lesson there. So what this says is a chemist uses 100 milliliters of 0.250 moles per liter of standard solution of ammonium oxalate. Now it says what mass of ammonium oxalate is needed to make the standard solution. So let's take a look. I always like to write down, like I said, what I'm given. There we go. So I'm given volume being 100 milliliters. Concentration is 0.250 moles per liter. And it's asking for the mass. Okay, so this is again, like I said, very similar to what we took a look at in our solutions concentration lesson just before. But essentially, I have two formulas that I can use. I can use C equals N over V, and N equals mass over molar mass. So my moles I probably need to calculate for, and then my mass, I can use my mass times my molar mass to calculate for that moles times molar mass gives us mass. So we can use that to calculate for our mass of substance. So let's just take a little look. I have my molar mass, which I'll do a calculation for quickly. So my molar mass of sodium oxalate, again, in the essence of saving some time, I'm going to just give you the molar mass of sodium oxalate, just so we have a little bit of time to save. So it's 134 grams per mole. And actually, that's not very accurate. When I'm dealing with molar masses, I should always have 2 decimal places. Okay, 134 grams per mole. So that's my molar mass. Now, again, I'm going to start with my volume and concentration to calculate for moles. So when I rearrange my formula to calculate for moles, my moles is equal to C times V. When I do this, I can calculate my concentration. So 2 moles per liter, and my volume, which is 100 milliliters, which is equal to 0.1 liters, because I need it in liters. When I solve for this, I should get 0.025 moles. Okay, so once I've solved for my moles, I'm going to solve for my mass. So my mass is equal to my moles times my molar mass. And I'm going to say that I have 0.25 moles, 0.025 moles times by my molar mass of 134.00 grams per mole. That gives me a mass of 3.35 grams. So that tells me how much mass I need to weigh out of my sodium oxalate, or my ammonium oxalate. Oh, which of course now, here I've calculated the wrong molar mass. Hold on, we need to go back in time. Just a minute. Because my ammonium oxalate, okay, hold on, my ammonium oxalate, the molar mass of that guy is 124.10. Okay, sorry about that. 124.10. So when I do that, I get 3.10 grams. Correction, 3.10 grams. All right. So again, you've seen a few examples like this. Let's take a look at one more here. Calculate the mass of sodium hydroxide needed to make 500 mils of a 10 mole per liter strong cleaning solution. So here we have our volume of 0.5 liters or 500 milliliters. Concentration is 10 moles per liter, which is very strong. And I'm looking to calculate my mass, and I probably need to solve for my moles as well. Sodium hydroxide, Na is 22.99, hydrogen is 1.01, and water is, oxygen, is 16.00. So when I add all of those entities together, I get a molar mass of 40.00 grams per mole. So, let's do my first calculation. N equals C times V. 10 moles per liter times 0.5 liters. This equals 5 moles per liter. Then to calculate my mass, I need my mass equals my moles times by my molar mass. And this is just moles, sorry. Moles times molar mass. This equals my 5 moles times my 40 grams per mole. I'll get my units in mass as grams. So 40 times 5 is equal to 200. So that is a very strong cleaning solution to make 200 grams of sodium hydroxide dissolved in half of a liter. Okay, now that we've looked at a few of those examples, I went through those quickly because we did go through quite a few of them with our concentration calculations lesson before. This portion is new though. We also can prepare solutions by dilution. Now, dilution is decreasing the concentration of an existing solution. So we dilute stock solutions to prepare our standard solutions. Now, stock solutions are just sort of solutions that you'll get from a manufacturer that have a set concentration of whatever entity that you're dealing with, and generally they're very concentrated. Okay, so they have a high amount of solute per the solvent. And often when you pour them out, they appear to be more viscous or dense or thick when compared to water. So they are quite concentrated solutions. Now, we refer to a dilute solution as one with a concentration of less than 0.1 moles per liter, while a concentrated solution is greater than 1 moles per liter. It's kind of a weird scale to look at, but it is dilute solutions is that 0.1 or less, and anything over 1.0 is very concentrated. And whatever is in between there is sort of exactly what I said, an in-betweeny solution. It's in between being a dilute and a concentrated. Now, how has our solute concentration changed? Well, essentially, we've decreased the amount of concentration, but the actual mass of solute has remained the same. We've just increased the amount of solvent, or our water in most cases. So we've added more water, but the amount of solute remains the same. So let's take a look at how we might solve for some of these questions. We essentially have a formula, and it's called VICI equals VFCF. So, or it's C1 V1 equals C2 V2. So essentially, initial concentration and volume equals your final concentration and volume. So concentration is inversely related to a solution's volume. So if you increase the concentration, the volume will decrease, or if you increase the volume, the concentration will decrease, which does make sense when we're talking about diluting a solution. Now let's just take a look at some calculations. It says water is added to 0.2 liters of a 2.4 mole per liter of ammonia cleaning solution until the final volume is 1 liter. Find the amount concentration of the final diluted solution. So I'm just going to write these things down. V1 equals 0.2 liters. C1 equals 2.4 moles per liter. Again, notice that we're dealing with amount concentration way more frequently than we are parts per million or our percent concentration. Amount concentration tends to be more important. V2 is equal to 1.0 liters, and our concentration is our big fat question mark here. So when we have V1C1 equals V2C2, we're going to rearrange our formula to solve for C2. Now when I do that, I need to divide by V1 and divide by V2 on both sides. So this results in C2 equals V1 C1 divided by V2, and that is my rearranged formula. So when I solve for this, I get my volume 1, 0.2 liters, times by my concentration 1, which is 2.4 moles per liter, divided by my volume 2, which is 1.0 liters. Now, when I plug these values in, I get a concentration of 0.48 moles per liter. As my final concentration. Now, again, I like to think logically about my answer to see if it makes sense as to if that sounds correct. So I initially started with 200 milliliters of 2.4 moles per liter concentration. So if I add volume, I expect my concentration to decrease. I did notice that my concentration went from 2.4 moles per liter to 0.48 moles per liter. So it did make sense. My numbers are logical in this situation. Let's take a look at just one more example at preparation of solutions through dilution. So 1 liter bottle of acetic acid is labeled with a concentration to be 17.4 moles per liter. A technician dilutes this entire solution to prepare a 0.4 mole per liter solution. Calculate the volume of this diluted solution prepared. So let's just write these values down again. I always like to write them down. That way I don't get any values confused and I don't miss anything. Okay, our initial volume and concentration is 1.0 liters, and our concentration is 17.4 moles per liter. Our concentration of our final solution is 0.40 moles per liter, and we're looking for our volume. So again, if we start with C1V1 equals C2V2, or initial volume and concentration, and our final volume and concentration, I'm solving here this time for V2. So again, I'm going to divide by my concentration 2, divide by my concentration 2 on my other side. So this is going to equal V2, giving us C1V1 over C2. So when I go to plug these values into my formula, I get my initial concentration of 17.4 moles per liter times by my initial volume, which is 1.0 liters, divided by my final concentration of 0.400 moles per liter. So when I plug these values in and I get my second volume, I get an answer of, gotta plug this into my calculator, I get an answer of 43.5 liters. So that is quite a large volume to reduce our concentration by that much. So they make a huge amount of our acetic acid solution here. So again, preparation of solutions through dilution. Now, as I finish up this lesson here, as always, I like to suggest to try to practice a few questions prior to going into completing an assignment. You do have an assignment for your preparation of solutions through the dissolving of a solid, as well as you have another solution on dilution calculations, so this C1V1 equals C2V2 formula. You may also be able to complete 2 labs on this preparation of solution. One is preparation of solution through a solid, and the other one is through dilution. And they're kind of linked together and related, so it's kind of cool to do. So, as always, if you need to go back, pause, rewind, take some additional notes, really dig into some of these examples, please do so now, and good luck.